Assalamu alaikum students. So today we are going to learn about buoyancy and stability. Let's assume that there is an object that is submerged submerged in a fluid as it is being shown here in this figure. Now the pressure is going to act on its surfaces. So it has two surfaces. There is a top surface and there is a bottom surface, which is this one here. At the top surface, the pressure that is going to act, we know the pressure, which is rho g h. In that case, pressure at the top surface is going to be density of the fluid g times s, which is this one here. And we know the force is basically pressure times area, so it is going to be rho f g s times a, and this is the force at the top surface. At the bottom surface, similarly, pressure times area, and the pressure here is going to be rho of fluid g, and the height is going to be s plus h times area. Now the net force that is going to act on it, net force is basically bottom force minus top force. If you think about pressure, the pressure is increasing downward because the height is increasing. So the bottom force, because of the higher pressure, is going to be higher than the top force. That's why I have written FB minus FT. So we know FB already, which is this expression, and the top force, which is this expression. When you subtract it, the result is going to be density of fluid times G times H. Times area. Now H into A, if you look at this figure, is basically the volume of the solid object. So F is basically rho F G and volume. Now initially, if you think about it, when there was no solid object there, then we had only fluid. When we submerged the solid object inside, it displays some volume of the fluid. So this volume is basically the volume of the fluid that is being displaced by the solid object, and that force here, and this force is known as buoyancy force. So the buoyant force acting on a body immersed in a fluid is equal to the weight of the fluid displaced by the body. And why it is the weight of the fluid displaced by the body? You know, M is basically rho V, which is the mass, and mg is weight. So the buoyant force acting on a body immersed in a fluid is equal to the weight of the fluid displaced by the body. Now look at this figure. This the resultant force is going to act upward, and it acts upward through the centroid of the displaced volume. So the buoyancy force is basically is the force uh, of the body when it is which is acting upward, and it is equal to the weight of the fluid displaced by the solid. So Fb is basically weight of the fluid, which is rho Fgv, and here V is the volume of the submerged solid object, and it should be equal to the weight of the body, which is equal to the density times G times total volume here. Now G cancels out with G, and we find out this expression here. Submerged volume over total volume is going to be equal to density of the body over density of the fluid. Now why we are saying the density of the average? Because like solid objects, they can have different density concentrations. So what we take is we take the average density. From this expression we can have three different scenarios. So scenario 1, I just say S1, which is scenario 1. Now the scenario 1, let's suppose the submerged volume is lower than the total volume. So submerged volume is lower than the total volume. It means that it is partially submerged in the fluid. In that case, what happened? I just give it numbers. I say submerged volume is 0.9 and the total volume is 1. So when it turns out, when we substitute these values here, we get density of the body is basically 0.9 of the density of the fluid, or in other words, density of the body is going to be less than density of the fluid, and density of the body is less than the density of the fluid. Submerged volume is less than the total volume, so the scenario would be that the body is going to float. So you can say that whenever the density of the solid is lower than the density of the fluid, then it is going to float. Now scenario 2. Scenario 2. Submerged volume is equal to the total volume. So V sub is equal to V total. So in that case, density of the body is going to be equal to density of the fluid. So when the density of the body is equal to the density of the fluid, the submerged volume is going to be equal to total volume. Or in other words, the body will be completely submerged in the fluid but suspended. It will not sink. Scenario 3 is when the density of the body is higher than the density of the fluid. In that case, the submerged volume is going to be higher than the total volume. Or in other words, the body is going to sink. So these are the three different scenarios, and I'm sure you have learned this in high school already, that whenever the density of the fluid is lower than the density of the whenever the density of the body is lower than the density of the fluid, it is going to float. If the density of the solid is higher than the density of the fluid, it is going to sink. And when it is equal, then it is going to be suspended, completely submerged but suspended. But if the density of the body is lower than the density of the fluid, will it always float? No, this is not the case, because sometimes you have seen that the boats, although they float, but they do sink. So then we come to the topic of stability. To understand about stability, there are three scenarios which are being shown here. The first scenario is a typical scenario of stability, that the system is stable. Let's suppose there is a ball as it is being shown here. I apply some force and move this ball here. And leave it. What will happen? It will come down, come to the initial place, because of inertia will go up, loses energy, become stationary and come back. So it will oscillate, and over time it will come back to its original position. This is a typical example of a stable system. Second scenario is naturally stable. And for the example is that a ball is placed on a flat ground. Let's suppose I apply some force that moves this ball on that surface. It will roll, and after some times it will stop because of the balance of forces. If you take the snapshot after its movement, it's the same. So this kind of system is known as naturally stable. The third scenario is a ball is placed on top of a hill. Now if I apply a force, it will roll down, but it will not come back. This is the example of an unstable system. Now to apply this concept on the object that are submerged in a fluid, whether partially, so I just draw a simple example. Let's suppose I have a rectangle. This is a rectangular solid object. Now it is going to have a center of gravity, and you know how to find out center of gravity of this. So it is something like this. So this is the center of gravity, which is G. This is the center of gravity of the solid object. Now part of this solid object is submerged in a fluid, and it makes a rectangle as well. So I try to find out center of this. So this is the center. So this center is the center of buoyancy. Now if the center of buoyancy and the centroid are in line, the system is known as stable. Now I draw a second scenario where it is slightly tilted to the right. Let's say just slightly tilted to the right. Same thing, we find out center of gravity. Say, say this is the center of gravity. Center of buoyancy is this one here. Somewhere, say, let me redraw it. Center of buoyancy. Now center of gravity, this is the line of center of gravity. Somehow it is just passing it through, but let's look at this figure. I'm having some trouble in drawing this. So that was the stable system. Now that ship has tilted slightly to the right. So this is the center of gravity, which is G. Now center of buoyancy has moved slightly to the right because there is more submerged volume inside the fluid. So we find out center of gravity of that, which is the center of buoyancy. We draw lines passing through the center of this, and they meet at a point, and that point is known as metacenter. Now remember this, if this metacenter is above the surface of the fluid, it will have a restoring moment. So now the ship is turning to the right, and if you look at the force which is being applied here, it is making it come back because of the buoyancy force. So this is basically creating a restoring moment. So ship is turning to the right, there is a restoring moment that is moving it, trying to move it back to the original position, like which is being shown here. So this kind of system is also known as stable system as long as metacenter is above the surface of the fluid. If it keeps on turning and its metacenter comes inside the fluid, then the ship is turning to the right because of its weight, and then we have a moment, and that moment, because of the buoyancy force, is also making it turn right. So it is basically the overturning moment now. So the system will become unstable. So to understand about stability, a simple rule is if buoyancy force and the and the center of gravity are in line, the system is going to be stable. You can say it's naturally stable. As long as if it is not naturally stable, if the metacenter is above the surface of the fluid, it will have a restoring moment and the system will stay stable. It will turn right, but it will go back to its original position. Because of the inertia, it will turn to the left but come back again. So it oscillates, and after some time it will come back to its original position. If the metacenter somehow comes inside the fluid, then it will create overturning moment and the system will become unstable. So we pause here for buoyancy and stability. If you have any questions, you can ask me now. Thanks a lot for your time.